Most of you appear to seem very confident with your do now. Again, from the other day, we learned how to write and balance nuclear equations. They are different from chemical ones in that you do generate a substance you did not have previously. What we're going to pick up with today, we'll continue with our learning goal. You want to be able to differentiate between chemical and nuclear reactions. We talked about that the other day. Remember, with chemical reactions, if you have an atom on the left side of the equation, it must be on the right side of the equation. We talked about the three main types of radioactive particles. What were they? Alpha, beta, gamma. You got it? You should be able to write and balance nuclear equations. I'll ask you that on your next quiz, not on the test. And today we want to learn how to explain and calculate nuclear decay rates. We're also going to talk about why certain radioactive particles are emitted or why electrons are captured. So we're going to take a look at a few other situations today. And this is where we left off in period 5. With radioactive decay, it turns out that most isotopes are not stable. Only 17% of all known isotopes are stable, so they don't decay spontaneously. When you're talking about the two subatomic particles in the nucleus, protons and neutrons, they are known as nucleons, and it is a strong nuclear force that actually acts on subatomic particles that are held or confined in a small space. And we're going to take a look at this strong nuclear force when we talk about fission and fusion at the end. But that strong nuclear force, think of it almost as a gate around the nucleus, is what keeps protons in the nucleus. Protons have what charge? Positive. So you have a lot of positive charge in the nucleus, and those positive charges will repel. As you get more and more positive charge there, you need more and more neutrons to balance out, not the charge per se, but to get in the way of some of that repulsion. And that's what you're going to see here. Nuclear stability is determined by the neutron to proton ratio. For example, atoms or elements with atomic numbers of 20 or less typically have neutron to proton ratios very close to 1 to 1. For example, if you consider helium or carbon or calcium, how would you get number of neutrons for helium? So you have 2 neutrons, and 2 is the atomic number, which is also equal to the number of protons. So you have 2 neutrons to 2 protons, or 2 neutrons to 2 protons, for a 1 to 1 ratio. I'm going to maintain the 100th place in that division. You'll see why in a little bit. Similarly here, you have 6 neutrons and 6 protons, 6 neutrons to 6 protons. If you divide those, you again get a 1 to 1 ratio. Same thing here, 20 neutrons to 20 protons, and that's a 1 to 1 ratio, a 1 to 1 neutron to proton ratio. And you find that 1 to 1 ratio when the atomic number is 20 or less in most cases. Some of them are ever so slightly higher than 1. As the atomic number increases, number of neutrons increases as well, and those neutrons are needed to produce that strong nuclear force to balance out the electrostatic repulsive force of all those positively charged protons. The highest you want that neutron to proton ratio to go is 1.5 to 1, and I'm going to pop a 0 in there, 1.50 to 1. Once it's greater than 1.50 to 1, that's when you have instability of the nucleus, and that's when it will undergo a decay series. For example, with lead 207, you're going to see that this ratio is slightly higher and again, this is 82 protons. Be careful with the neutrons. Make sure that you subtract. That's 125 neutrons. 125 divided by 82, and that's going to give you a neutron to proton ratio of about 1.5. Can't see a thing. Oops. And that is ever so slightly greater than 1.5 to 1. This is as high as you want it to go, and this is as low as you want it to go. Yeah, go to the 100th place. It'll be easier to watch for it. And what you're going to see here is the number of neutrons on the y-axis, the number of protons on the x-axis. Here's helium with its neutron to proton ratio of 1 to 1. Here's a neutron to proton ratio of 1 to 1 along this line right here. Here's the 1.5 to 1 along this line. Anywhere on these lines or within these lines, this is known as the band of stability. So anything in this region touching those lines is stable. Anything below the 1.0 to 1 ratio or above the 1.50 to 1 ratio is unstable, and that's when it's going to undergo some type of nuclear decay series where you'll emit maybe beta or alpha, etc., with the goal being to try and generate a neutron to proton ratio within the band of stability. The band of stability typically ends with bismuth 209, although some leads are not within the band either. So all elements with atomic numbers greater than 83 are radioactive. So all isotopes of those elements will be radioactive because you will have a situation where your neutron to proton ratio is not within the band of stability. And the type of decay it undergoes depends on whether you want to increase or decrease that neutron to proton ratio. It says atoms lying above the band of stability have too many neutrons as compared to protons. Below the band, they have too many protons compared to neutrons. Beta emission has the effect of increasing the stability of a neutron-rich atom by lowering its neutron to proton ratio. Remember, when you have beta decay, for example, let's say that we had californium 252, atomic number is 98, and let's say we wanted to emit a beta particle. One beta particle is probably not going to do it, but it could emit more. That increases the number of protons. Mass number doesn't change. So if you compare the neutron to proton ratio here, 252 minus 98 is 154 neutrons to 98 protons. So if you divide that, you get 1.57 to 1. 252 minus 99 is 153 neutrons to 99 protons. And you have 153 divided by 99, and that's going to be 1.55 to 1. So emitting beta particles will lower the neutron to proton ratio. So if you emit a lot of them, then hopefully at one point you'll be within the band of stability. So beta emission will reduce or lower the neutron to proton ratio. So you would want beta emission if you were above the band of stability. And I know some of you didn't quite get that yet. Now for atoms lying below the band of stability where that ratio of neutrons to protons is less than 1 to 1, there are two common radioactive decay processes that occur. One is positron emission. When you emit, you are releasing, so that particular radioactive particle will go on the right side of the equation. And you also can capture an electron. Now when you capture something, you surround it, you grab it. So with capture, it goes on the left side of the equation, and I'll show you both examples. With positron emission, this is going to look just like a beta particle, but you have a +1 here as opposed to a -1. For example, it says carbon 11 emits a positron, and you have it there, but I'll show you how that's derived. You've got carbon 11. You're going to emit a positron. You have +1 here. It looks like a beta, but you have +1. Carbon has an atomic number of 6, which we can get off the periodic table. What +1 is 6? 5. Mass number doesn't change. And as a result, you're going to generate boron now. And what happens here is your neutron to proton ratio, 5 divided by 6, was 0.83 to 1. And here it's, going to be 1.20 to 1. So positron emission has the effect of increasing the neutron to proton ratio. You don't have to memorize that. Know what a positron is and know how to write the equation, and from there you can interpret. So if I asked you what the neutron to proton ratios were, you could show me, and if I asked you whether it increased, decreased, or remained the same, in this case the neutron to proton ratio does what? Increases, because 1.20 is greater than 0.83. Another way you can increase the neutron to proton ratio is to capture an electron, and it really has the same effect. Again, you're going to increase that neutron to proton ratio. So with electron capture, and again, when you capture something, you surround it. For example, rubidium-81 captures an electron. So the electron shown here is on the left side of the equation. 37 plus -1 is 36. Mass number doesn't change. You generate a new substance due to the fact that it has a different atomic number. So there's a lot of different ways you can do that. Dead in the middle of your notes here, I have a whole bunch of problems that will make you review all of those key concepts, alpha, beta, and gamma. Some of the pieces we talked about the first day, and I do have all of them worked out, and at the end today we'll work through it. I would like for you to try 4 and 5. See if you can do 4 and 5, and then we'll check your answers to make sure you're doing them correctly. I'll write them out here. And you'll see a question similar to this on your quiz, probably a little easier. we doing? Are you on 4 or 5? Okay. Ready? In regard to 4 and 5, let's see how we did. Here's 4. There's your N to P ratio. This is why it's outside. And then on 5, did you calculate the neutron to proton ratio correctly after writing the nuclear reaction? Yes, piece of cake? All right, and I would say 5 is similar to what you might see. I might throw in an alpha particle or 2. Yep.
For number 5, why did U turn to E?
Because when you emit a beta particle, what plus -1 makes 92? That's 93. When you change the atomic number, you look at the periodic table to get the element. Yes? Go ahead.
Why don't you put 2 to make it less than 1.5?
What?
Like, why don't you put 2 beta particles?
Did I ask for 2?
No. How many did I ask for?
It just says write a balanced nuclear equation for the beta decay, so it didn't specify how many. You can assume 1. If it wanted 2 or 3, it would say 2 or 3. Like in the next problem in 6, it says plutonium-245 releases 1 alpha and 3 betas, so that's how you would know how many. All right, and I'll give you a chance to work on those problems toward the end, and I think you'll be very comfortable with that. The other concept that we want to cover today are radioactive decay rates. I think you might have seen those in middle school as well as fission and fusion. Radioactive decay rates are measured in half-lives. And a half-life is the amount of time required for half of the radioisotope's nucleus to decay. So when I think about half-lives, I like to think about it this way. If I have 10 grams of a sample, and the half-life, let's say, is 20 days. In 20 days, or after 20 days, I will have 5 grams of that sample. And in another 20 days, I will have half that amount, or 2.5 grams of sample. And in another 20 days, I will have half that amount, or 1.25 grams of sample. So here's where I'm starting with 100%, cut it in half is 50%, cut that in half is 25%, cut that in half is 12.5%. This has undergone 1, 2, 3 half-lives. How much time has passed after 3 half-lives? 60 days. So the total time elapsed is 60 days. So one way to figure out how much sample remains is to just chain it along. There's another way to do it that's probably a little bit easier that we'll take a look at. It says the half-life of the radioisotope strontium-90 is 29 years. If you had 10 grams of strontium-90 today, 29 years from now, you would have 5 grams left, and the decay continues until negligible or barely any strontium-90 remains. That is shown graphically here. You start with 10 grams or 100%. After one half-life of 29 days, you have half that amount, 50% of it. After another 29 years, you have 2.5 grams. After another 29 years, etc. So you can chain it right through, or this formula here is very useful with these types of calculations. The amount of substance that remains is equal to the initial amount times 1/2 to the n power, where n is the total time that has elapsed over the half-life. So in regard to the example that we did previously, if I wanted to know the amount remaining, that's equal to the initial amount that you started with, 10 grams, 1/2 to the n power, where n is the total time elapsed, which is 60 days, over the half-life, which is 20, which is 1/2 to the third. Now, as a reminder, before we push that forward, what's 2 to the 0?
0.
No, it's 1. 2 to the 1 is 2. 2 squared is?
4.
2 to the third is?
8.
2 to the fourth?
32.
And that's as far as we're going to get. So 1/2 to the third power is 1/8, and 1/8 of 10 grams, 10 over 8 or 5 over 4 is 1.25 grams. So you can do it either way. Usually the kids like this method because it's quick. Now, each radioisotope has its own characteristic half-life, and there is a whole list here of radioisotopes. And they really do have a very large range of half-lives here. If we were going to look at half-lives of substances commonly used in the lab, for example, phosphorus, P32 has a half-life of about 14 days. P32 is used to label DNA. DNA contains phosphate groups. You learned about phosphate. PO43- is a phosphate ion. S35 is another radioisotope I've used in the lab. That's going to label up amino acids. There are 2 amino acids of the 20 that contain sulfur. That is a half-life of about 87 days. I-125 is another radioisotope that I've used in the lab. That one's very dangerous. When you're exposed to a lot of radioactivity in the lab, they can tell, because in the lab you wear a film badge, and that shows how much radioactivity you're exposed to every month. At the end of the month you take the film out and you drop it in to be developed, and then you put a new film badge in, or a new piece of film into your badge, and they look at how much radioactivity you're exposed to see maybe if you're not doing things very carefully, or maybe you have some type of leak in your lab. There are three very simple problems here. Let's work through the first one together to make sure that we can calculate the amount of remaining isotope. In the first one, it says iron 59 is used in medicine to diagnose blood circulation disorders. The half-life of iron 59 is 44.5 days. How much of a 2 milligram sample will remain after 133.5 days? Let's get that information down and you'll see just how easy it is to process. Why would you use iron 59 to diagnose blood circulation disorders? What's the protein found in your blood? It starts with an H. Hemoglobin. And inside hemoglobin, if you look at the structure, there's an iron ion, so isotopes of iron would be useful. It says the half-life is 44.5 days. The initial amount that you begin with is 2 milligrams. And the total time elapsed, abbreviated TT, is 133.5 days. So the amount remaining is equal to the initial amount, 2 milligrams, 1/2 to the N, where N is the total time, 133.5 days, over the half-life, 44.5 days, and that's 3. So 1/2 to the third power is an eighth. 1/8 of 2 is 2/8, or 1/4, or 0.2500 milligrams. Maintain your sig figs based on what was given. If you don't like that method, you can chop it in half each step of the way, and you'll get the same answer. You have 1, 2, 3 half-lives that have been undergone. That's the N. So you can do it either way. It doesn't matter. They're both very simple. And that might be a question on your quiz.
What is TT?
Total time elapsed. Sorry. Maybe it's not the greatest. TT also means test tube in the lab, but easy peasy? All right, you try this problem at the top of the screen, highlighted in, what color you want? Blue? Blue it is. Now blue is easy to see. It's pretty. How'd we do? Did you get it? Did you get it? Are you ready?
Yes.
What'd you get? Did you get what I got? Yes, yes? All right. The other question is very, very simple. It says a radioactive element has a half-life of 2 days. Which fraction represents the amount of an original sample of this element remaining after 10 days? So they don't specify an amount, they just ask for a fraction. So you can assume the initial amount is 1, and then you just have 1/2 to the n power, where n is the total time over the half-life. So you'd have 1/2 to what power? 5, because you have 10 over 2, and that's equal to 1/32. Just don't make like a silly math error. That is not 1/10, and that's why I did your exponents at the beginning. All right, one thing we have seen previously this year, for example, the other day in the lab, we reacted sodium bicarbonate with hydrochloric acid to generate sodium chloride, water, and carbon dioxide. And we heated this reaction to speed up its rate. So whereas heat is a factor that increases the rate of a chemical reaction, you're not going to find that with nuclear reactions. And as a result, half-lives of radioisotopes are constant. And so some radioisotopes, such as carbon-14, can be used to date substances. You can date rocks and things like that, where you probably learned a little bit about that in middle school. The other thing I do want to mention is fission and fusion. Fission, splitting apart, fusion, putting together. And I've got a cute little video that really illustrates fission versus fusion. And we'll take a look at that. There are 2 videos. This one I think is more entertaining. We'll take a look at this one.
And nuclear fusion before. Many of you have heard the terms nuclear fission and nuclear fusion before. Nuclear fission means the splitting of atomic nuclei. This is the process by which energy is generated in nuclear power plants. With fusion, it is exactly the other way around. Here, the atomic nuclei amalgamate. One result of nuclear fusion shines down on us from the sky. This is the energy that stars like the sun emit. But what exactly happens in these 2 processes? And why is so much energy released in the course? To be able to understand this, we first have to recap what the structure of an atom looks like. In the center, there is the atomic nucleus. That is to say, the thing that is split, or that amalgamates with another nucleus. Nuclei consist of neutrons and protons. The protons are positively charged. The neutrons have no charge, hence they are neutral. Thus, the atomic nucleus as a whole is positively charged. Around the positively charged atomic nucleus, so-called electrons are whirring around, like in a kind of cloud. They are negatively charged. So now let us look at what happens when nuclear fission takes place. Here, the atomic nucleus is hit by a single neutron that's flying around. The impact causes the atomic nucleus to split into 2 new nuclei. Each of them
And again, fission, breaking apart.
takes part of the electrons with it, so that 2 new atoms are formed. In the case of some very large atoms, a few neutrons are additionally released. When uranium atoms are split in a nuclear power plant, this usually involves the release of 3 neutrons. These can then affect the next fission processes in a chain reaction. And finally, energy is released, and very much of it at that. 1 kilogram of naturally occurring uranium has the energy of 12,000 liters of mineral oil, or of almost 19,000 kilos of hard coal. But where does this energy come from, and why is it so much more than in the case of other energy carriers, such as oil and coal? Let us recall, besides the neutrons, the atomic nucleus only consists of the positively charged protons. Now, equal charges repel each other, similar to the equal poles of 2 magnets. The fact that the If one now tries to force two of these protons together, these two would have to repel each other due to their equal charge, as in the case of magnets. When talking about atomic nuclei, this is referred to as the so-called Coulomb force. This force acts as if each of our protons had a fence around it, trying to keep off other protons. Like fission needing a force that overcomes the rubber band of strong interaction, fusion also needs one that forces the protons so closely together that the fences are pulled down. And once this happens, and the protons come too closely together, strong interaction comes into play again, and makes sure that the two amalgamate into a new atomic nucleus. As in the case of the nuclear fusion on the Sun, it is in fact 4 hydrogen atoms, that means 4 protons, that amalgamate to form a helium atom. But as the latter only has room for 2 protons in its nucleus, the other 2 are released, similar to the excess neutrons upon the fission of uranium. And of course, this also involves the release of a lot of energy, even more than upon nuclear fission. It would only need 1 single gram of fuel, or the hydrogen isotopes deuterium and tritium, to gain as much energy as from 12,000 kilos of hard coal. This is why scientists try to develop power plants in which energy is won from nuclear fission. But how is the Coulomb force, meaning the fences around the protons, overcome? This happens by speeding up the atomic nuclei, and that happens when they are subjected to great heat and/or pressure. The more pressure is available, the less heat is needed. Sooner or later, 2 atomic nuclei will hit each other at such great speed that the force of the impact will overcome the Coulomb force, and the protons will no longer repel each other. This is also what happens in the Sun, where 15 million degrees and a pressure of 200 million bar are necessary to amalgamate the hydrogen atoms. In a fusion power plant on Earth, we would even need 150 million degrees, as we have a lower pressure than inside the Sun. However, to this day, we have not been able to generate such high pressure in a fusion power plant. If you would like to learn more about this topic, just watch our videos. What actually is radioactivity, or types of radiation?
And so the distinction between fission and fusion should be clear. And basically what she said is written out here, so you don't want me to read this to you. You really have to be careful with exposure to radiation. Radiation, X-rays, more powerful type of rays can cause mutations in DNA, which may only affect you, but mutations in the egg and sperm cell lines could affect children in the future. So we always want to be very careful with radiation exposure. That's why you wear sunscreen outside. That's why when you get your teeth x-rayed at the dentist or an arm x-rayed if you fear you might have broken it, and you will always use protective clothing. Not protective clothing, protective metal. Lead typically will mold around you and block whatever type of ray they're going to zap you with. But you always want to be careful when working with radiation. This is one of the reasons why kids can't work in too many labs as high schoolers, because you have to be 18 to work with any type of radioactivity, and a lot of labs do involve radioactive material. Also, if you're working with organics, like the organic chem labs at FAU or somewhere else in the area, they'll usually only take you once you're 18. Some of them will take you a little bit younger. And it is a good thing to do during the summer if you're interested. There are a tremendous number of summer internships available. I highly recommend that you apply for them. I've got a tab on Edline, and I try and update that whenever something comes in, or I can put it in Google Classroom if you prefer. But that's your nuclear chem. What I'd like you to make sure that you complete, probably not before tomorrow because you have your test tomorrow. There are 8 problems in your notes. We've already done 2, so you should be able to do a couple right now. And classwork 3.x, which most of you got. If you didn't get it, you'll want to come up and do it. You can do all of those problems as well. And that is a brief description of nuclear chemistry that is an honors concept, but not something you'll see in AP, although you could see it in college chem. So you really want to understand the radioactive particles, why certain radioisotopes emit alpha versus beta versus positron, etc., and understand how to calculate the amount of substance remaining.